is life and we need to save it, conserve it, please don't waste it. Use it when it's necessary for cooking, drinking and beating the heat. Save the water, save the water, save the water.
Everybody needs to come together to conserve and to save our water. We can do it, yes we can do it.
Water is life, or we can lose it.
Pay for the service when you use it.
We can do it. Save the water, save the water, save the water.
Using the Sophia water treatment plant as an example of some of the studies that have been carried out at various water treatment plants that have a similar process. If you look at the diagram below, and we have hard copy printouts of the presentation so that each member of the audience can have for their reference. The Sophia water treatment plant is designed primarily to remove iron. As I mentioned before, we have iron removal plants or groundwater plants, which are designed to remove iron, manganese, dissolved gases such as hydrogen sulfide. These are gases that can affect the smell, the odor, the taste of the water. So this treatment regime you're seeing here is characteristic of the different areas that receive well water as their source of treatment. And these areas would include not only Sophia, but also Central. We have all of the East Coast, Better Hope, Monrepo, Friendship, East Bank, Region 2, Berbice. This is a similar process. Each treatment plant may have simple or slight modifications, but the heart of the unit operations would be these processes here. So the first stage you're seeing here is called the aeration. And the aeration process is a very integral process for groundwater treatment. It's basically where the air, the natural air from the atmosphere, is introduced into the water to provide what is known as dissolved oxygen. So the oxygen from the air is entered into the water to oxidize all iron and to strip away all dissolved gases so that the water can have an improved taste, an improved odor. As a matter of fact, removal of all odor and removal of iron specifically. After the aeration process, there's a retention process so that the air and the water can react, and then a filtration process. Now, I want to focus a bit here. The air and lime, this is a chemical that is added to improve the pH of the water so that all iron can be oxidized effectively. Now, I guess many of you would have seen, for example, treatment plants on the East Bank or right there on the back road in Mandela, and you would see water just flowing down in a series of trays. That is the aerator. It's where the air is introduced into the water for the aeration or the oxidation process. After the retention, we have the filtration process where all oxidized iron, manganese, or other metals are removed, and this is where we disinfect the water right after the filtration process, and the water is then stored and distributed to customers. Now, a few observations have been made specifically at the Sophia water treatment plant, and these observations have been characteristic in many of the water treatment plants of similar nature. And one of the first things that our managing director, Dr. Van Westchilds, did as soon as he took office was to give us a mandate of improving these processes countrywide. And one of the first plants that we would have started this with is the Sophia plant, and we've observed that over a few years, that's over the last 3 to 5 years, the iron removal efficiency of the water treatment plant has been extremely poor. As such, the water quality would have been not as optimum as it should have been, thus contributing to the supply of aesthetically unpleasant water. The overall average iron removal efficiency prior to the interventions was only 24%. In other words, the plant was only producing prior to 2015 and up to the early part of 2016, the plant was only removing 24% of iron. The iron concentration recommended by the World Health Organization is 0.3 milligrams per liter, and at the Sophia water treatment plant, the iron was coming out at 0.95, which is 3 times more than the recommended. So this warrants sufficient interventions that were needed to be done so as to improve this situation, so as to have a better quality of water. As you would see here, if you were to zoom in quickly year by year, we have a bar chart here representing the red bars represent the raw water, that's the water as it comes from the wells, and the blue bars represent the treated water. As you would see in the graph throughout, that throughout 2014, all of the final water would have been non-compliant with the WHO requirement for iron. As a matter of fact, the overall iron removal efficiency for the entire year of 2015 was only 41.5%, which is insufficient for proper quality water. In 2015, we had a similar situation where the overall iron removal efficiency was just 15%. Only 15% of iron was removed for the entire year of 2015. And of course, you would see month by month the difference between the water coming into the treatment plant and the water leaving was not that significant. Likewise, in 2016, the overall iron removal efficiency was just 29.5%, which was extremely poor in terms of the performance of the water treatment plant. So after conducting this study, we decided that interventions definitely have to be done so as to improve the water quality. And these studies were done not only at the Sophia water treatment plant, but at other water treatment plants so as to improve the quality of the water. And as you would know, I don't have to tell you what effects the iron can have on your tiles, your laundry, your bathroom mirrors, etc. And therefore it's necessary for this parameter and the overall treatment process to be improved. So as we mentioned, we zoomed into each treatment process as we saw in the box diagrams, the aeration process, the filters, the lime dosing, and we found that there were issues that needed to be fixed. The lime dosing system was inoperable, and the management had to resort to manual dosing of the lime, which was still inadequate. This is prior to the interventions that would have been done, of course. The dissolved oxygen levels, that is the amount of oxygen from the air being entered into the water, was still inadequate for optimum oxidation of the iron. The filter media, that is the sand that is found within the filters, was less than 20% of the required amount for the filters. So the filters definitely needed attention. Hence the performance of the filters and the overall process was extremely poor during this period. And this period, as I mentioned, specifically 2014, 2015, and parts of 2016. And as we saw in a few slides ago, the overall average iron removal efficiency prior to the intervention was only 24%. So what were some of the interventions that were done? And as we know, some of the parameters that would guarantee appropriate or optimum water quality based on the World Health Organization standards or guidelines would be the pH, turbidity, iron, and of course our microbial quality of the water. So one of the first things that were done, if you look at the diagram, the graphs that we have here, before any optimization, we had to optimize the lime dosing system, which was performing poorly and in some cases was inoperable in some of the plants. Prior to the interventions, we see here that the pH, which is a measure of the acidity of the water, which is necessary for the iron to be removed, the pH was consistently below 7. And these measurements were taken specifically in 2015. The pH was consistently below 7, but after the interventions, we found that the pH was now in a more optimum range, above 7, which is necessary. The iron is better removed at a pH range between 7 to 7.5, approaching 8. So we had a more consistent value there, and to date, the pH continues to be in this range. What were the interventions that were implemented? A new mixer and motor a mixer for the preparation of the lime system, was installed at the treatment plant to aid in the mixing of the lime slurry. And that lime slurry was required so that you can have a consistent dosing of the lime solution or the lime suspension to the water. Of course, a lot of laboratory tests had to be conducted and calculations done so as to effectuate the correct dosages. And as you can see here, as of August 17th of 2017, when all the interventions would have been completed, the pH has since been achieving the optimum value of above 7. Another intervention that was done is in the aeration process. The aerator is a series of trays, as you can see here, where the water flows from one tray to the other, where you have oxygen from the atmosphere being introduced or added to the water. What was done was the addition of Paul rings. Paul rings are these random plastic packing that we see here implemented. And as you can see the design, they have several holes in them so as to increase the oxygen to water ratio, to increase the surface area. In other words, increase oxygen transfer into the water. So Paul rings were added to the aerators to increase the surface area of the air-water contact, hence improving the oxygen transfer into the water. And as a result of this, there was an 80% increase of oxygen transfer. So prior to this intervention, the oxygen transfer was very poor, hence the iron removal overall was very poor. And thus, with the implementation of the Paul rings, we now have an 80% increase in oxygen transfer. And as you would know, better oxygen transfer, the better the removal of iron and other dissolved gases like hydrogen sulfide, methane, etc. And this is very critical, because if this isn't done properly, you would have odors and tastes in your water in certain areas, and therefore it is important for the removal of these gases and metals. Another major intervention that was done in many of the treatment plants throughout the country was the optimization of the depth of the filter media. The filter media is a sand that is used of specific specifications in terms of diameter, weight, etc., so as to remove all particulate matter from the water. And as you can see here again, the red bars represent the raw water coming out of the wells, and the blue bars represent the final treated water after filtration process. And as you can see, the final water is consistently below 0.2 milligrams per liter. The WHO requires us to have below 0.3, and we're consistently below 0.2 milligrams per liter ever since the intervention. So the depth of the filter medium is optimized, 26 inches as required, and the iron levels monitored each day since the rehabilitation of the filters. The iron levels are now in compliance with the WHO guidelines, and the overall water quality improved. As you can see the figures below, the average raw water iron coming into the system is about 1.42 milligrams per liter, and the amount of iron leaving the system is below 0.2, which is 0.18 milligrams per liter, which represents an overall iron removal process of 86% plus or minus 10%. So we're removing as much as 96% of the iron, which is practically all of the iron that is present in the water. Now, the interventions have been done, but to ensure that the water quality is maintained and there are no slippages, a 24-hour mini lab has been implemented here in Georgetown, and we have a few other mini labs throughout the country. In Lethem, places like Cotton Tree, Lima in Region 2, Linden, Region 6, we have mini labs. And the aim is to have mini labs in every administrative region for the purpose of continuously monitoring the water quality on a daily basis, and so that if any slippages occur, it can be addressed at the very moment before the situation escalates. So these are little snippets of of water samples being taken in the fields, equipment used to measure, and this was an actual reading of iron, and we got 0 iron in one of our samples there. Microbe samples taken in the field, and one of our analysts taking or analyzing the water quality data. And as we mentioned, that the Georgetown mini lab operates at round the clock, 24/7, and testing is done on an hourly basis. So for example, here at Shelter Belt, we have every hour on the hour test samples are being collected, and we're going to see in a few where these samples are collected, what areas samples are collected in the treatment process after each stage of treatment, as well as in the fields, in the distribution from various homes, so that we can ensure that the consumer is actually getting the quality of water that they should be getting, and that there's no compromise between when the water leaves the treatment plant and when it gets to the customer. This table briefly shows some of the samples that would have been collected during the course of this year. And as I mentioned, samples are analyzed every single day in the laboratory. We have a central laboratory as well as several mini laboratories in each region. And here we have a few of the samples collected in the region, in the distribution system in the community, and the water quality that has to do with the aesthetic quality as well as the microbial quality. What is important to note that there was no E. coli detected. E. coli is one of the pathogens or microbial contaminant that is hazardous to health. And the WHO, the World Health Organization, requires this to be 0. If for any reason any E. coli is detected, then interventions are made immediately with regards to disinfection, resampling, and ensuring that the water quality has been improved immediately. As you can see also, the turbidity and the iron in color, and the turbidity and color speaks to the clarity of the water. The iron, as we mentioned, also affects the clarity and the overall taste and aesthetic of the water. You can see here that the majority of the samples are in complete compliance. We have 2 samples here in East and West Rhineville that we have fluctuating iron values, and as such, a similar study is being conducted at the treatment plant that is supplying this area, so that interventions can be made to correct or to improve the water quality. Notwithstanding the fluctuating iron values, the turbidity and the color are extremely low. In other words, the clarity of the water is still very good and in compliant with the required WHO standards for these areas. And again, all samples are without E. coli. This is a simplified diagram of the treatment scheme for typical surface water plants. And this in particular is for the Shelter Belt plant, which is this, the plant in this compound, the water treatment plant in this compound. Now, as I mentioned before, the surface water would include rivers, lakes, creeks, and in the case here at Shelter Belt, the Lamaha Canal. And as we know here in Guyana, we have very brown or very highly colored surface water. And therefore, that water has to be submitted to an intensive treatment process to remove those organic material which is contributing to the overall color of the water. So very quickly I'll go through the stages so that you can have an idea what each stage represents with regards to treating the water. So the raw water coming from the canal, in the case of Linden it's coming from the Demerara River, in the case of Bartik it's coming from the Mazaruni River, and they have very similar characteristics in terms of the organic matter, the color, and the amount of solids in the water. The first stage of treatment would be, and we're focusing first on the blue boxes, the first stage of treatment would be the flash mixing, where 2 chemicals typically used worldwide in water treatment, alum and lime, are added so as to remove all organic matter, remove all turbidity, and all substances causing the water to be colored. After the flash mixing, which is a very rapid mixing process, it goes to the flocculation process, which is a slow mixing process allowing the particles to attach to each other and be able to accumulate wait and settle. So right after the flocculation process, we have the sedimentation, which is divided into the primary and secondary sedimentation process. In some treatment plants, we just have one sedimentation process. And here, you have all the particles settling out. So all of the particles causing the color would be able to accumulate and settle out. And then it passes to the filters where those that haven't settled out are now filtered out of the water. So at this stage now, you would have clear water, where in the case of shelter belt, we add a few wells to this water, we disinfect and store for distribution. So this is an overall synopsis of what goes on at each treatment stage. It is important to monitor the water quality at each stage of treatment so that we can have an idea of how each treatment process is performing and if it's performing optimally and what interventions need to be done as soon as possible. So you would have things like parameters such as pH, iron, turbidity, color, which are all chemical and microbiological water quality indicators to see how each treatment process is performing so that we can have an assessment of the overall performance of the treatment plant. And of course, at the end of all the treatment process, before the water leaves the water treatment plant, it is submitted to a full analysis of microbiological, chemical, and physical analysis so that we can ensure that the water is compliant with the WHO standards. So as you can see here, all of after each stage of treatment, there's testing done, as well as in the distribution network in the communities to ensure that the water quality is safe. We have here a table and two pictures to show the raw water quality that comes in from the canal, which you can see is characteristic of the rivers, the Lamahar Canal, and the creeks, and the water, what it looks like after it passes through the entire treatment process. Here you can see that the water is characteristic of high color and turbidity and other parameters that are causing it to have this poor aesthetic value, but after treatment you would expect very clear water. If for some reason during our test we detect the water quality is not in compliance with what it should be, then interventions are made immediately to correct the situation. The table above shows the WHO guidelines for the aesthetic parameters, which would be the turbidity, iron, and true color. Now, WHO requires that the water has a turbidity of less than 5. In 2016 and prior to 2016, this turbidity of the final water here at Shelter Belt was not compliant consistently with the turbidity. It was 6, just above. However, in 2018, we managed to have this below. And these results are as a result of interventions done during the course of 2016, 2017. And now we have water that's compliant with the turbidity, the iron, and the true color, as opposed to previously. Now, we've spoken intensively of the water treatment process, or water treatment processes, and the quality interventions that would have been done to improve water quality. A few other interventions that would have been done with regards to the quantity and supply of the water would be increase in water supply hours and pressure. Specifically at the Shelter Belt treatment plant, which is the largest treatment plant in the country and is primarily responsible for the major part of Georgetown, the water treatment, the water distribution hours have been increased from just 17 hours a day to a complete 24 hours a day. So previously, in 2015 and prior to 2015, you would have noticed that the water supply would have been shut off by 10 p.m. in the evening. But as of 2015, 2016, we have increased this water supply to 24 hours. So if you feel the need to have a shower at 2 a.m. in the morning, water supply is now increased, or has since been increased to 24 hours. And also the pressure. We have increased the pressure from 10, and even at times less than 10 psi, which is pounds per square inch, to now about 20 psi consistently throughout the day. So areas that wouldn't have been receiving water to their second and third floor can now benefit from that because of the increase in supply and distribution hours. Likewise, the pump stations. We have pump stations where the water coming out of the wells are not passing through a conventional treatment process, but receive an alternative type of treatment, and in some cases, because of the quality of water, do not require treatment. These pump stations, the water supply and the water distribution has been increased to a full 24-hour supply. It has been increased from just 17 hours to 24 hours. And this includes Festival City, North, Kingston, Turkine Industry, for Georgetown, and all the other pump stations that we have on the East Coast, the East Bank, and throughout the country. They've been increased to a full 24-hour supply. Of course, there are areas that, because of the capacity and the growth of population, there may be some challenges with regards to that, but the aim is to have all operational facilities supplying water 24 hours. And just quickly, what this chart is showing, that in 2014, where you notice the red and the yellow blocks, this would be the level of service that would be characteristic of a very poor or even below poor level of service in terms of the pressure that is supplied in different areas throughout Georgetown. In 2014, you would see that there were lots of yellow and red blocks. However, in 2018, we've managed to eliminate this completely, where we have the blue blocks depicting excellent level of service, and the green blocks indicating adequate level of service. So throughout Georgetown, because of the increase of pressure, the increase of water supply and distribution hours, the level of service now has been increased throughout. Apart from the treatment plants, apart from the water quality analysis done after each treatment process and in the distribution, testing has been done extensively in the schools throughout the country. So we've had very good collaboration with the Ministry of Education in this regard, both GWI and the Ministry of Education. And in Georgetown, we have managed to clean 100% of the primary and nursery schools. We've cleaned and we have disinfected, tested the water prior to the cleaning and after the cleaning to assure that the water quality is completely safe. Likewise, throughout the country, testing is ongoing. We've had 100% cleaning in some of the regions already, and other regions are still in the process of cleaning. And whilst cleaning is being done, testing is also done concurrently to ensure that the water quality is where it needs to be done. So standard operating procedures have been developed and circulated to all of the regions so that all operators or persons involved in this process knows how to clean, how to disinfect, and how to collect samples so that the labs can test these water quality samples to ensure the water is safe. If in any case after cleaning the water quality is still not safe, then cleaning has to be done again until the water is safe and interventions done to ensure that no contaminated water is entered into the system, and also that after storage the water quality is not compromised. So here we've compiled just a snippet of the many schools that would have been cleaned in Georgetown throughout the East Bank, the East Coast, throughout the country. And as you would see here, all of the schools are now having 0 E. coli, very low total counts, and as such, based on the World Health Organization guidelines and standards, the water is now clean and safe for consumption. This has been done in all nursery schools and all primary schools. And the move is to have all secondary schools, even though secondary school students are more conscious of the water quality, nonetheless, all schools is under the purview of being cleaned and determined safe for consumption.
For the service when you use it,
We can do it. Save the water, save the water.